about in any two spots of the angle.
All right, thank you, Yara, and thank you to all the organizers for putting together a great conference. I know it's a lot of work, and I know we all appreciate, especially those of us who can actually be here in person. So yeah, today I'm going to be talking about work I've been doing with John Joseph and Henrik over the last couple of years that has finally culminated in a paper that appeared on Monday, and that is tackling 6-loop n=4 super Yang mills. I think it was 3 years ago I was up here talking about 5-loop supergravity. In a couple of years, I hope to be up here talking about 7 loops as well. So the general outline of what we're going to be talking about is first some motivations and introductions, then some interesting tree identities that are very simple observational tree identities that turn out to be very powerful when you start embedding them inside of loop diagrams, thinking about them in terms of cuts, and then applying them inside of the method of maximal cuts. So that will lead into talking about how these new identities work inside the method of maximal cuts and what they can do for you in calculating higher loop diagrams. Finally, I'll discuss 6 loops briefly. You have to understand everything in 6 loops is enormous. I will not show any explicit 6-loop numerators, just a couple of nice pictures. So the main motivations for the talk, the main motivations for the project. Well, why would we want to calculate 6 loops? Well, because we want to calculate 7 loops at some point. Now that's kicking the can down the road a little bit. The reason we really want to do 7 loops is this ties into counterterm arguments related to supersymmetry and symmetry arguments, where a bunch of traditional supergravity people and supersymmetry people have predicted an unprotected counterterm that could appear at 7 loops in d=4. Now, the interesting thing is that similar arguments predict counterterms for lower supersymmetry at lower loops. In particular, these arguments generate unprotected counterterms in n=4 and 5 supergravity for L = n-1, so at 3 and 4 loops. But explicit calculations by SYM and collaborators have shown that these counterterms actually carry a 0. Via explicit calculation, you calculate the loop amplitude, and there is no counterterm there. Also, there's some interesting observations that I've made with some of my collaborators about improved behavior in d=4 as a result of special kinematic shifts. So there's a lot of evidence on both sides, or there's a lot of interesting things to say potentially as we go and look at 7 loops. And it seems to be evidence that the d=4 actually does something special for you in terms of supergravity and counterterms. So how's the progress been going so far? Well, 1 and 2 loops were handled in the 80s and 90s. Then 3 loops took until the 2000s, 4 loops later in the 2000s, and like I said, 5 loops was finished a couple of years ago. Hopefully we don't have such a long gap in the next couple of steps we have to take. And that's sort of the goal that we're going to be trying to tackle here, finding new ways of making this progress faster. So if we think about calculating amplitudes, the traditional textbook method would say you need to do Feynman diagrams. Sum up a bunch of Feynman diagrams, you get the amplitude. But especially in the case of n=8 supergravity, there are more Feynman diagrams than could fit on any reasonable computer, any reasonable cluster, any supercluster you could ever conceive of. So we need to do something that helps contain the explosive growth of Feynman diagrams. And the first thing you would say is, well, we should work with cuts. This is an old story. I think everyone in the room and everyone on Zoom has heard this to some extent, but we need to focus on cuts because they contain the minimal amount of data needed for the theory. However, even focusing just on cuts, the state sums are very difficult. In supergravity, there's 256 states per propagator that you've cut. Now you have to insert that multiple times inside of any given cut diagram. This is still explosively bad. The solution that SYM and company have found for this is focusing on the double copy. so that we can figure out some way to write gravitational amplitudes as a square of Yang-Mills. So that buys us a square root factor here. But there's still the problem that in super Yang-Mills, the state sums are still hard. It's not the bosonic part, but it's the fermionic part. You get gamma traces. For instance, at 6 loops, you can end up with 28 gammas in a single trace. You don't want to do that on the computer every single time you need to evaluate something. It's also explosively bad. So one of the tricks, or there's been a collection of tricks that have been used in the past. So up through 4 loops, there's a combination of color kinematics duality and tricks for recursing special classes of cuts that together allow you to specify the entire integrand in terms of a small set of diagrams, and those diagrams can be evaluated using these special tricks. Now, there was a problem that's encountered with color kinematics at 5 loops that prevents the entire integrand from being written back in terms of a small set of masters, which means that we can't use this second to last line. We can't combine color kinematics with special tricks anymore because there's no color kinematics to help us out, at least as far as we know currently. But we still need to combat all of these problems. We don't want gamma traces. We don't want massive state sums in supergravity. So we need some new recursive tools, some new tricks to handle a much broader class of cuts that will hopefully span everything we need at 6 loops and hopefully at 7 loops as well. So the first of these is a very simple identity. And the idea for this identity is that in 4-point ordered Yang-Mills, the 4-point Yang-Mills tree only has an S and a T channel pole. The U channel is in the other color ordering. But if in the ST ordering, we try and sit on the U channel pole anyway, something interesting happens. The first thing is, well, the amplitude is dimensionless. And even as we take this limit, we have to respect all of the symmetries of the external particles. So the only thing that can happen is that we get an insertion of identities, an insertion of delta functions. And that essentially means that the diagram that used to be planar now disconnects into a non-planar crossing where we have to identify the diagonally opposite states. So in the case of Yang-Mills very specifically, you can just go grab your favorite 4-point tree amplitude representation, take this limit, and the thing that pops out is proportional to epsilon1.epsilon3 times epsilon2.epsilon4. You can then supersymmetrize this. So any of the states pairing up will either give you the contraction of their wave functions or 0, depending upon essentially if the contractions make sense. So if one's a fermion and one's a boson, that's fine as long as the fermions are identified and the bosons are identified, etc. Now this is nice, but there's a slight problem to it that I will, for use in loop amplitudes that I'll come to later. So there's a second identity that we can derive. And we actually derive it in terms of the previous one. And this is an identity that maintains planarity. So for the X identity that I just talked about, you're disconnecting it, but in a non-planar way. So now we want something that maintains planarity. And the observation is, first of all, that if you take this combination S13 times 1324, and then you take the X identity limit, this P3 goes to P1, this is some factorization channel with a specific 0 momentum exchange. And also you can combine this, this 0 momentum exchange factorization with the 4-point BCJ relations, so the amplitude relations. And then on one side, you get this factorization with 0 momentum exchange, but on the other side, you get a disconnected diagram because the other side is just the X identity. So what ends up happening is that you can take a special limit on a tree amplitude. This goes on to the factorization channel, but then you're taking the factorization, the channel where the factorization actually has no momentum propagating through it. And that just gives you some prefactor times a disconnected diagram. Again, you can just crank through the example in Yang-Mills with 4 gluons, and it comes out exactly as you expect. And all of the super partners also do exactly what you expect. Zeros in the right places, delta functions in all the other places. The other nice thing is that this can extend to supergravity. Obviously, when you set it up as on the right-hand side of the diagram, it's all 3-point amplitudes or 2-point amplitudes. And so everything will just square to gravity right away. I should note that this looks like the H rule to a lot of people. Or sorry, we call this the H identity, and this looks like the rung rule to a lot of people. And the statement should be that this is the thing that makes the rung rule work. This is the reason why the rung rule works, is that the rung rule is kind of an accidental simplification of what's going on here. And I'll show the real details about why this works at loop level, or why this is useful at loop level in just a second. So before we start imposing these things and using these things at loop level, I should talk a little bit about how we actually build up an integrand. For many people in the audience, this will be familiar and might be a slightly strange presentation. For the others, this is maybe one of the hardest things to actually explain by speaking about. Makes much more sense once you start to compete with it, but I'll do my best. And the idea is we're going to use the method of maximal cuts, which has been developed by Zvi and Lance and David, and then a number of other people afterwards. So we're going to build up a systematic construction of the loop integrand from the cuts, avoiding rational functions as much as possible. So the first thing we need to do is enumerate our diagram basis. So essentially, we start with a collection of cubic vacuum diagrams. These are well studied by mathematicians. There are lists of them available. And then you attach 4 external legs in all possible ways to these diagrams. And then slowly start collapsing internal legs, noting all of the unique topologies you find on the way. And we label each of these diagrams by how far away from the cubic diagrams they are. So cubic diagrams, we call their cut level 0, they're maximal cuts. If there's one quartic vertex, that's the next to maximal cut, k equals 1. Next to maximal is 2 quartics or 1 cubic, and so on. For each of these diagrams, we associate 2 bits of physics. One of them is a cut, which is a gauge invariant rational function. This is the factorization channels. This is the data from your theory. And the other is a numerator. And this thing behaves similar to a Feynman diagram, but it is essentially free for us to choose as long as it helps us reproduce the cuts. And then finally, we have to go through the process of building these numerators so that we reproduce the cuts out of the numerators. And essentially the way this works is that at each cut level, we inherit the poles from the previous cut level by summing over the numerators over the uncut propagators. And that gives us some rational function R that comes from data we've already determined. And then there's some truth cut, some actual calculation from field theory. And the difference between the actual cut and the sum over previous numerators divided by their uncut propagators gives us some new local correction that we need to account for on a given diagram. So like I said, the R's, throughout R's are going to be some rational function that we've calculated from previous numerators in the method of maximal cuts, so from previous K levels. C is going to be our cut, which is the full gauge invariant rational function that we're trying to match. And then the P is the new local polynomial, and that's the thing that we're trying to construct. So we're trying to determine the P's. We need some way to evaluate the C's. And the R's are just stuff that we've already evaluated coming along for the ride. So the first thing that we will look at is we're going to embed the X identity, this uncrossing identity, inside of the method of maximal cuts. And essentially the idea is we can calculate any of the C's, any of the cuts directly from a special kinematic limit on some higher loop, but planar cut. This is useful because planar cuts are in general significantly easier to calculate. And planar integrands in general are significantly easier to calculate than in the non-planar case. And essentially the idea is if we have some, for instance, 6-loop diagram, everywhere that there's an edge crossing in the 6-loop diagram that we want to calculate, we instead identify that as a 4-point amplitude in some higher cut. So in this example, we have the L equals 6 cut on one side of the equality, and on the other side of the equality, there is some kinematic limit of some 10-loop cut where each of the colored lines are taken to have identified momentum. And there's a couple black lines that are identified also. But basically, all of the 4-point crossings, you identify the opposite momentum on either side. Now, there's a couple of technical challenges with this. The first two go kind of hand in hand, and that is that actually calculating how many edge crossings you have and which ones they are is not a particularly efficient operation. It's asymptotically NP hard, and you start running up against this bound actually rather quickly. And that is in strong tension with the fact that for each of the crossings, you need to go up in a loop level. And so as I've demonstrated here for L equals 6, this is even a bad choice of crossings. You can get one better, but for L equals 6, if you pick a bad choice, you land on L equals 10. If you picked an even worse choice, you'd end up on L equals 11. And you can see very quickly that maybe not at 6 loops, but at 7 loops, you would be forced to start evaluating L equals 11, L equals 11 and higher cuts. And that's a problem because essentially the best explicit answers we have in the literature come from Jake and friends at 10 loops. This is also, there's also the caveat that this only works in Yang mills, so it doesn't port to gravity nicely like the H identity will. So the H identity is a little bit more computationally intensive, but it avoids some of these pitfalls. So the idea here is that the H identity doesn't let us directly evaluate C, but it lets us evaluate P on a bunch of constraining limits. So on the limits where we take one of the cut legs to have 0 momentum flow, we end up projecting down onto a lower loop cut. Since the way that we approach these problems is we go loop by loop anyway, that means that we can evaluate various limits of these polynomial factors, of these local contributions in terms of lower loop data. So in the example here, on the left-hand side, we're taking the dashed line to have 0 momentum flow. So then the red line, which we're going to call J, and the blue line, which we call I, those two lines, the lines on either side of the dashed line get identified. And we end up being able to write the limit of the local contribution is equal to the limit of the rational function, the stuff that we've calculated already from the previous K levels, plus some contribution that comes from the lower loop. And the lower loop contribution is exact. It's just that now we have to figure out how to merge all of these conditions that we get from the limits. So a couple of the challenges here is we need to merge these conditions. This is not an exact calculation, but it is a merger of a bunch of different constraints. And we also need to handle a large number of evaluations of the lower loop cuts. Because you end up needing to do this for every leg in the diagram. So the constraints are the interesting part. So the basic idea is that on a given cut, you can fix the basis of momentum invariance. So you have some basis of ISPs, and you have some collection of stuff that is killed by the cuts. And what we want to do is we want to write the cut essentially just in terms of the stuff that's not killed by the cut conditions. And then we also, once we have fixed the basis for these objects, we note that this limit of sending one of the momentum to 0 is some projection operation on the basis. So you're projecting some linear combination, you're projecting out some specific linear combinations of the variables. And we can handle this, this set of constraints that we get from the limits in a couple of ways. The first is the sort of obvious brute force approach. You just write down an ansatz. You know what basis elements you have. You have a bunch of operations you do on this basis to give you some known conditions. You just crank through. P is some polynomial ansatz. Your projection operations give you some constraints, and you solve the constraints. However, we can do slightly better. And that is that we can interpret the constraints that we have as forming polynomial ideals in some geometry. So we note that for each of the projections, that since we can calculate each of the projections, we also know that the final polynomial is always going to be the sum of the projection plus something that's in the kernel of the projection. And this defines an element inside of a polynomial ideal. And what we actually know is that the polynomial we're after, the final object we're after, has to live in every single one of the polynomial ideals individually, which means it has to live in the intersection of all of them. This is a well-defined algebraic geometry problem. You can essentially just pipe this entire thing into singular and get back out an answer. There's some minor technical details about some slight additional constraints and degree bounding, but this is essentially a systematic solved problem. So we can go on, we can start calculating 6 loops. We write down a bunch of vacuum diagrams. We put legs on the vacuum diagrams. We get 1.1 million diagrams we have to go check. We evaluate the H rule, the H identity. So we take a single diagram and we take every individual leg soft, generate either all of the constraints on the ansatz or all of the polynomial ideals, merge them together, and eventually we get an integrand. So we go from 1.1 million potential contributions, and of that, only a small fraction actually have non-zero polynomials, so a non-zero numerator. It's around 150,000. And some of you in the room might be concerned that I've put non-zero numbers on all the k values, on multiple k values for the numerator. So the easiest way to handle this for now, because it's so big, is that we just leave the numerator in terms of contact contributions. So there's color factors hanging around on these things. They're essentially DDM color factor, arbitrary DDM factors for each of the vertices that are higher than 3 point. The nice thing is, with a little bit of clever writing, but zero compression other than clever writing, this thing is about 600 megabytes. It fits on a CD, not so much on archive, but it does fit on a CD. And a little bit of statistics about how big some of these things are. The largest cut is one of the maximal cuts. It has 62,000 terms. The shortest numerator is the ladder diagram and all of its friends. That has 1 term, which is s to the 5th. A little bit of the statistics, you can just take an average of all the lengths of these things, and it averages about 90 terms. So, okay, I'm not putting anything on the slides, but you could imagine 3 slides of polynomial going by, and it might fit. So we have a 6-loop integrand. Now what do we want to do? The first thing we would like is to do some UV integration. There's some well-defined critical dimension that we should be able to reproduce. That'll be a future check that we're going to look into. And part of it is that we need to prep the tools for supergravity. So supergravity at 6 loops is slightly less interesting than supergravity at 7 loops. Mostly it's going to be a trial for various tools, tricks, techniques, understanding, getting the computers to work together properly, because this is going to be a big problem to tackle as we move forward. One of the other things we need to work on is improving the efficiency for 7 loops. Off the top of my head, most of the 6-loop calculations, the 6-loop maximal cut calculations take between 1 and 10 seconds. The initial 7-loop calculations take over an hour. So that's a gap that we need to bring down, because there's also a factorial growth in the number of diagrams to check. So one of the interesting things is this intersection of ideals story is actually highly reliant on seemingly superficial choices. So what do you call your first variable? What do you call your first ideal? This is just an inescapable fact of modern computational algebraic geometry. So understanding good choices there is important. Also understanding how many limits you need to actually evaluate. From the ansatz perspective, you can just evaluate, solve until you've solved everything. From the ideals perspective, that's a little bit more difficult. And if we want to use an ansatz, there's obviously been significant improvement. We're using finite fields for our solution. We're using finite fields for our solution set, but there are even further improvements to inverting matrices that it might be useful to implement. So some combination of this improving the intersection techniques and improving the ansatz. We're also looking into applications to other theories. This is avoiding, the idea here is we're avoiding state sums. So there's a lot of places where calculating cuts in more efficient ways would be useful. For instance, in QCD, there's also some tie-ins with some work that I do with Oliver Schlotterer and other people at Uppsala on the open string effective action at loop level. And this might be an interesting way to start allowing us to bootstrap higher end loops in the open string effective action. Finally, as I said, it's not a cubic representation. So one of the things we'll need to do is study a cubic representation, some finite number of steps to get us from this contact representation to a nice cubic representation. Then we can start using generalized double copy, studying color kinematics duality, because we now have another place where it potentially won't work, but studying why it doesn't work. And with that, I will conclude. So questions?
Questions here, Enrico? Yeah, so this H rule, does it apply only in the cubic graphs if you really have this like H channel, or can you remove, like from these contact diagrams, if you have a 4-point vertex, can you remove any rung?
So we haven't investigated that fully. I have poked at it a little bit in the open string effective action case, and in that case, you can remove one of the legs that goes into a higher point vertex. You end up with a 0 condition essentially. So when you remove a rung that goes into a higher point vertex, you should get 0 rather than some actual contribution. This is still a useful thing, as you know. The 0 conditions can still be quite powerful in constraining things. It's just that if you have absolutely no cubic, like pairs of cubics to remove from, then you get a fully homogeneous constraint. So you're missing some overall scale.
Maybe I have one question.
Yeah.
Maybe more like, I don't know if exactly for SYM, but in general. So you start always from scratch from constructing the amplitude. Is it possible first to really start with the planar limit as like given and then build on that, or that wouldn't be?
So that's essentially would be the idea of doing an entire an X identity focused construction. So then you march up in loops in the planar limit, and then build the contact, like construct the cuts, the deeper K cuts for very high loops, and then use limits on those to get you the non-planar cuts at lower loop level. So that's one of the ways you could start with planar cuts. The other would involve kinematic Jacobi's of some form, and that has difficulties starting at 5 loops, as we know.
Questions on Zoom? There is Mao. The robot was up. Yeah.
Hi, Alex. So you talk about identities X and H for 4 points. Is there any motivation to look at like higher point, 5-point identities?
Potentially, it's much more difficult. So far we haven't needed them, but it could be useful, especially if we want to do a direct construction of gravity, which that's probably a long ways off. So there is a possibility for new relations, but at this point we don't need them.
Okay, thanks.
Okay, more questions? Thanks a lot, Alex.